Hello students, welcome to the statistics class. In today's class we shall deal with movements. So what are movements? Movements are popularly used to describe the various characteristics of a frequency distribution such as average, dispersion, skewness and kurtosis. As we had discussed while at the beginning of the chapter analysis of univariate data, uh, there are four measures which describe a data, that is measures of central tendency, measures of position, measures of dispersion and measures of skewness and kurtosis. So all these describe a particular characteristic of the distribution. So movements summarize them in a simpler form. Okay, now let us look at the types of the movements. So movements are classified into two types here. The first one is raw movements. The second one is central movements. So let us look at them one by one. So first one is raw movements. So movements about any arbitrary point A are known as raw movements. They are denoted by mu r dash and given by mu r dash is equal to summation of x minus a to the power r divided by n, where r is equal to 1, 2 and so on. So if you take movements about any arbitrary point in the given data, then such movements will be called as raw movements. Okay. Next, the second one is central movements. So movements taken about mean are known as central movements. They are denoted by mu r and given by mu r is equal to summation of x minus x bar raised to r divided by n, where r is equal to 1, 2 and so on. So if you take movements from mean or with respect to mean, then such movements are called as central movements. If you take movements with respect to any arbitrary point or any assumed number in the given data, such movements will be called as raw movements. Okay. Now some of the central movements derived here are the first movement about the mean is 0. That is mu1 is equal to summation of x minus x bar divided by n will be 0. Obviously, here the numerator is nothing but the one of the properties of arithmetic mean. That is, if you take deviations from arithmetic mean and if you add those deviations, your answer will be 0 is the point here. Hence, the first movement about mean will be 0. Okay. Next, the first movement about 0 will be mean. If instead of x bar, if you take 0 here, then summation of x minus 0 will be x itself. So summation of x by n, summation of x by is nothing but the formula of mean. So if the first movement about the 0, then it will be a mean value. Next, the second movement about the mean is variance. That is, uh, here in the place of r, you are changing the values 1, 2 and so on. So here in the place of r you have substituted as 1, so that results in the 0. If in place of r if you put 2, then summation of x minus x bar square divided by n, that is equal to sigma square. Another interesting thing about this here is, again this is another property of arithmetic mean, where it says summation of x minus x bar whole square is least. That is, if you square the deviations, then those value will be least values. So summation of x minus x bar divided by n, this is nothing but the formula for variance, and if you add the root here, it will be standard deviation. Okay. Next, similarly, the third moment about mean is measure of skewness. So if you substitute r is equal to 3 here, then this will be the measure of skewness, which we are going to study in the later part. And last but not the least, if you substitute r is equal to 4 here, then that would be mu 4 is equal to summation of x minus x bar divided by n. This is called as the kurtosis. Hence mu 1, mu 2, mu 3 and mu 4 together they are called as central movements. Okay. Next, Carl Pearson's beta and gamma coefficients based on moments. So, Professor Carl Pearson defined the following coefficients based on the first four central moments. So, Carl Pearson's beta and gamma coefficients. So, here beta tells us the skewness of the distribution and the beta 2 tells the kurtosis of the distribution. Okay, so based on the three moments there, mu1, mu2, mu3 and mu4, Carl Pearsons have derived these beta and gamma coefficients. So for a distribution, these two represent the skewness and kurtosis here. Okay, so beta 1 is equal to mu3 square divided by mu2 cube. Also, gamma 1 is equal to root of beta 1. Similarly, beta 2 is equal to mu 4 divided by mu 2 square, and gamma 2 is equal to beta 2 minus 3. Okay. So here beta 1 tells you whether the distribution is skewed or whether it is symmetrical. If your beta value is 0, then it will be a symmetric distribution. If it is not, then it will be a skewed. Similarly, beta 2 will tell you whether it's the symmetrical curve or a normal curve. Okay. In other words, beta 1 is the measure of skewness based on moments, and beta 2 is the measure of kurtosis based on moments. Okay. So this was a brief introduction to moments. Now let us look at the last measures, that is the measures of skewness and kurtosis. Okay. So previously we had studied that the measures of central tendency and measures of dispersion, we learned that a single value that represents the entire mass of data and the extent of the spread of values in a data from that single value. Okay, so we studied arithmetic mean, geometric mean, harmonic mean, median and mode, which gives you a single number that represents the entire mass of the data. And to check the reliability of the data, sorry, the measure of central tendency, we use standard deviation, that is a measure of dispersion, to check how or what extent of the spread is among the data or the observations in the given data. But we may come across distributions which are very different in their nature, yet their central tendency value and dispersion value is same. So when we can't decide about which data to be selected on the basis of central tendency, then we check the spread of the data, spread of the observations among data, and upon that we decide which data should be selected. What if two distributions are having the same mean value or central tendency value and the same dispersion value or standard deviation value? For example, in the given two data sets here, x is 3, 9, 15, 21, 27 and 33. Frequencies are this here. Similarly, for the second distribution, you have frequency different here. So the mean and variance here for the two distributions are 18 and 7.22. Okay, now the two distributions have the same mean and standard deviation, but if you observe them here, the structure is very different. Here the frequencies uh, are spread across evenly here, so 10, 30, 60, 60, 30 and 10, whereas here the frequencies are 10, 40, 30, 90, 20 and 10. Here they are distributed evenly, but here in the second distribution the frequencies are distributed very unevenly. Okay, uh, despite this, the mean value and the standard deviation value are same. Okay, so thus arises the need to study whether the scatter around the central value are symmetric or not. Now comes the question whether the scatter of the data, that is, the scatter is symmetric or non-symmetric. The distribution which is not symmetric is called as a skewed distribution. So whether the data is distributed properly or not, the frequencies are distributed evenly or not. If you observe here, it starts on a lower point and then steadily increases, and at 60, 60, and again from here it starts decreasing at the same rate. It increased in the same rate and it decreased in the same rate. So here the values are distributed evenly, whereas here the first value is 10, next it is 40, again 30, again 90, again 20, and 10. So the distribution of the frequency is very odd here. So it is not in a certain pattern. Here the distribution of the frequency is in the certain pattern, that is increase and then decrease. Here increase, then decrease, then sudden increase, then sudden decrease, and then after the lowest value. So we can see that in the two distributions, one distribution is having frequency distributed evenly, another one is not so evenly distributed frequency. Hence arises the question of the symmetricity of the values. Hence, this lack of symmetry is called asymmetry or a skewed distribution. Then what is skewness? Skewness refers to the lack of symmetry or asymmetry. So if a distribution is lacking in proper distribution of the frequencies, then such a distribution will be called as a skewed distribution. So the study of that skewness or the lack of symmetry is called skewness. Okay. So when will you say that a distribution is a symmetric distribution? So symmetric distribution means an evenly distributed data. Okay, so when will you call a given distribution a symmetric distribution? So uh, if the distribution has mean, median, and mode identical values. Suppose for a frequency distribution, if we calculate the mean, median, and mode, okay, and if all the three are same, okay, if all for the same data, if you compute mean, median, and mode, and all the three are same answers, then we say that the distribution is a symmetric distribution. Second one, the median is equidistant from lower quartile and upper quartile. That is, for distribution there are three quartiles, Q1, Q2, and Q3. So that if the distance between the Q1 and Q2 as well as Q2 and Q3, if it is the same, then we call it as a symmetric distribution. Suppose the Q1 for a given distribution is 20, Q2 for a given distribution is 50, and for the same distribution if Q3 is 80, then 80 minus 50 will be 30 is equal to 50 minus 20, that is 30. 30 is equal to 30. So distance between Q2 and Q3 is as same as Q1 and Q2. Then we call such a distribution as a symmetric distribution. Or another condition is when you plot the distribution on a graph, then you get the shape of a bell. Okay, that is like this. So when you plot the uh, variable values and the frequencies and it gives the shape of a bell, then we call such a distribution as a symmetric distribution. Okay. Next, the types of skewness. So what are the different types of skewness? First one is positively skewed distribution or positive skewness, and the second one is negatively skewed distributions. So in a distribution, if the mean, median, and mode value are not equal, or if the quartile positions are not equidistant, and if you draw the distribution on a graph paper, it doesn't form a shape of a bell, then it is a skewed distribution. Now, there are two types of skewed distributions here. One is positively skewed distribution, another one is negatively skewed distribution. The diagrams showing types of skewness along with positions and of mean and median and mode. So let us look at the diagrams here. So the first diagram here is of a positively skewed curve. So here the curve is such that for this distribution the mode value will be the smallest, median will be greater than mode, and mean will be the highest among all the three. So mean will be highest, followed by median, and then followed by mode. So for a positively skewed distribution, the mode will be the lowest value and the mean will be the highest value. Next, the second curve, negatively skewed curve. Here for this distribution, mean will be the least value, median will be greater than mean, and then mode will be the highest value among all the three. So for a negatively skewed distribution, your curve shape will be like this, which indicates that mode is the highest for the given data and mean is the lowest for the given data. And at last we have no skewness, that is a symmetric distribution. For a symmetric distribution, mean will be is equal to median will be is equal to mode. So all the three values will be identical. Okay, so we are going to deal with some examples on positively skewed and negatively skewed curves. Okay, so now comes the measures of skewness. So measures of skewness may be absolute or relative. So while studying dispersion, we come across two set of measures there. One is absolute measures, another one is relative measures. So similarly here also we have absolute measures and relative measures. Absolute measures are expressed in the units of the distribution. So whatever the units of the given values in the distribution, the answers will be in the same measures. That is, for example, kilograms, or height in terms of centimeters, or weight in terms of kgs, pounds. If it's a distance, then it will be terms of meters or kilometers, etc. If the data has units and if the result is expressed in that units, then such measure is called as absolute measure of skewness. Such measures cannot be used for comparison with another distribution with different units. So suppose if you have two distribution with two different units, say one is in terms of kilograms, another one is in terms of pounds. So you may be not able to use absolute measures of skewness here. So for the purpose of comparison, it is necessary to have a relative measure of skewness. So for comparison of two distributions, we need them to be free of units. So that is, it should be expressed in terms of percentages or ratios. So we go for relative measure of skewness. So these relative measures are called coefficient of skewness. Some of the important measures of skewness are Karl-Pearson's coefficient of skewness, Bowley's coefficient of skewness, and measures of skewness based on movements. So for relative measures, we have three formulae here. One is Karl-Pearson's coefficient of skewness. The second one is Bowley's coefficient of skewness. And the third one is measure of skewness based on movements. So let us look at them one by one. So first one is Karl-Pearson's coefficient of skewness. So it is given by mean minus mode divided by standard deviation, x bar minus z divided by sigma. So for a given distribution, if it has only one mode, if it is unimodal, then we go for this formula here. That is, we find out the mean, we find out the mode value, and then we find out the standard deviation value. And after that, we go for this formula. Okay. Suppose if the given distribution has mode ill-defined, or if the mode for the given distribution is not defined properly, or if it is bimodal or multimodal, then we cannot use this first formula here because we need only single value of mode. Okay, but as we previously have studied and know that sometimes the distribution can have more than one mode value. So in such cases, we cannot use this formula here. Hence, we go for this formula here. We go for this formula here. Carl Pearson's coefficient of skewness, that is 3 into x bar minus median divided by sigma. Suppose for a given distribution, if mode value is not defined properly, then instead of finding out mode, we find out the median. Okay, so for that given distribution, we find out mean value, we find out the median value, and then we find the standard deviation value, and we use this formula here, that is 3 into mean minus median divided by sigma. So this is your Carl Pearson's coefficient of skewness. Next we have Bowley's coefficient of skewness. So Bowley's coefficient of skewness is based on quartiles. So we used all the three quartiles here, Q1, Q2 and Q3. So Bowley's coefficient of skewness is given by Q3 plus Q1 divided by minus 2 into Q2 divided by Q3 minus Q1. So Q1 is your lower quartile, Q2 is the median or the second quartile, and Q3 is the upper quartile or third quartile. Okay. Next, similarly, we have measures of skewness based on moments. So as we previously dealt with moments, so beta 1 refers to skewness and beta 2 refers to kurtosis. So beta 1 here, it is given by mu 3 square by mu 2 cube, where mu 3 is the third central moment and mu 2 is the second central moment. Also, for this distribution, gamma is nothing but root of beta 1. It is the measure of skewness. So these are the three methods of measuring skewness, coefficient of skewness. Let us look at the problems or few example based on the three formulae. So let us look at an example here. Calculate Carl Pearson's coefficient of skewness. So the first important thing that you have to do is check whether the distribution has only one highest value or multiple highest values. So the frequency here we have 14. So there is only one highest frequency here. So for a given distribution, the mode value z is equal to the x value corresponding to the highest frequency. So here highest frequency is 14 and its corresponding value is 30. So the mode value here is 30. Okay. Here it has been wrongly misprinted. Here z as 3. It is 30. Next, we have to compute now the mean as well as the standard deviation. Okay. So the mean value here is given by x bar is equal to summation of fx divided by n, and standard deviation is equal to root of summation of fx square divided by n minus summation of fx divided by n whole square. So if we compute the mean here, then f into x will be 1320 divided by 42, which is 31.429. And for standard deviation, we need two columns here, fx and f into x square. That is, we already have the fx here. We have to square the x values and then multiply them with the respective frequencies here. So that would be 47,200 divided by 42 minus 1320 divided by 42 square. So f into x square here is 10 square into 4. That is 100 into 4, 400. This is 20. 20 square is 400. So 400 into 8 is 3200. Next 30 square is 900. 914 is 12600. 40 square is 1600. 1600 into 10 is 16,000. And 50 square is 25,000. 25,000 into 6 is 50 square is 2500, and 2500 into 6 is 15,000. So in total it is 47,200. So which sums up to 1123.809 minus 987.782. 0.782. That is 11.663. So we have mean value is equal to 31.429, mode value is equal to 30, and then we have the standard deviation value 11.663. So hence Karl Pearson's coefficient of skewness is given by x bar minus z divided by sigma is equal to 31.429 minus 30 divided by 11.663, that is equal to 0.123. So now the interpretation of the answer is very important here. Okay, so if this answer is in terms of positive number, that means the distribution is positively skewed. That is, if you draw the graph here, then you will get the curve as we discussed in the previous segment. Next, so you can also check whether a distribution is positively skewed or negatively skewed, because for a positively skewed distribution, mode will be the least and mean will be the highest. So here the mean value is highest as compared to the mode value. Hence the distribution is positively skewed. We have to write the conclusion here. This is a 10-mark question. Okay. Next, let us look at another example of a continuous distribution here. For a continuous distribution, we don't have x values directly, so we take the midpoints here. Okay. So again, we have to check whether for a given distribution there is only one highest frequency or multiple highest frequencies. So here we observe that there is only one highest frequency, that is 30. So we can say that we can use the Karl Pearson's first formula here. Okay. So that is x bar is, so first we find the mean. X bar is equal to summation of fx by n, that is 4240 divided by 80, which is 53. Next we find the standard deviation here. So standard deviation, we can go for either this method or u dash method. We can go for any method of standard deviation. The answer is clearly 22.605. And lastly we find the mode value here. So for a continuous distribution, first we have to find the class belonging to the highest frequency. The highest frequency here is 30. The class belonging to the highest frequency is 40 to 60. So therefore its formula is given by z is equal to L plus Fm minus F1 divided by F2 into Fm minus F1 minus F2 into C. So substituting all the values here, L is the lower limit, which is 40 here. Fm is the frequency of the model class, which is 30. F1 means the frequency preceding the model class, that is 12. F2 is the frequency succeeding the model class, that is 20, and C is the width of the model class, which is 20. So when you sum it up, the final answer is 52.857. And Karl Pearson's coefficient of skewness is given by x bar minus z divided by sigma, so which is 0.00663. Again we observe that this number here is a positive number. Okay, also because the mean value is 53 and mode value is slightly smaller than mean, that is 52.87. Hence the distribution is positively skewed distribution. Okay, so this is how we have to write the conclusion of the given problem. Next, we look at another problem here, that is calculate the skewness. Now again observe if the data has multiple highest values here. Yes, it has multiple highest values, 40, and again here it is 40. Hence we cannot apply this formula to the given data here. Hence instead of finding the mode, we have to find the median here. So we have to find mean, standard deviation and median for the following data. Okay, so we find the mean by our traditional formula, summation of fx divided by n, that is 5890 divided by 150, that is 39.27. Similarly we find the standard deviation here, which is 22.808, and finally we find the median value here, which is 45. So Karl Pearson's coefficient of skewness is given by 3 into x bar minus median divided by sigma, which is minus 17.19 divided by 22.808, which is minus 0.753. Here the answer is negative. Therefore, the distribution is negatively skewed, is our conclusion here.